Good morning, good afternoon, or good evening, everyone, depending on where you are. Welcome to the fourth webinar of four-part webinar series we are conducting with the release of PSCAD version 5. Previously, we had webinars on general introduction to version 5, PRSIM and initializer tools, and high performance features of version 5. If you missed them, and want to go through them, please check our website. They will soon be available there. I'm Rohita, and I will be introducing new models and model enhancements to the existing models in version 5. Along with me, I have several colleagues joining me for this webinar. They will assist me answering any questions you may have. If you are attending to the live webinar, feel free to ask questions in the questions window during or after the webinar. And as always, you can also use the support desk after the webinar, send an email to support@pscad.com. If you're attending to a rebroadcast of this webinar, please send an email to our support desk. I will be introducing new models and model enhancements by groups. So I'll be switching between the slides and PSCAD application back and forth. First group of components I would like to show is related to power electronics. Some of you may have seen the MMC related components that was available in the intermediate library in 4.6. Now they are in the master library, and we also created a new 6-pulse wire group model that supports any transformer phase shift. So let me switch to PSCAD. So you can find these components in the power electronics section. There is the MMC full bridge, MMC half bridge, MMC full bridge, MMC half bridge, and the firing pulse generator for the full bridge, firing pulse generator for the half bridge, and associated controls. There's a multidimensional carrier signal and multidimensional comparator, and a new sorting component. So this could be used to select the which wants to fire in the MMC bridge. This is the new 6-pulse bridge component. The only difference with the previous component is instead of asking for a specific transformer connection, now you can give the what is the phase shift in the transformer. So this component is, except this parameter, all the other parameters are one-to-one compatible with the old component. So you, with this, you can have a phase shift of 7.5 or 15 degrees. So to make a, let's say, 24 pulse or 48 pulse converter. So I have a simple set of examples. This is the Segre benchmark. So it's using the new component, just specifying the what is the phase shift in the transformer. And the example for the MNC bridges. It's using 38 level MNC, half bridge component, and here is the fire impulse generation, and sending the fire impulses to the MNC components. Okay. Next group of components I like to show is the digital controls or discrete controls. So some of these components, derivative, integrator, PI, and the poles, real differential and lead lag, their parameters are in, it's asking in the continuous domain parameters, not the coefficients of the Z domain. So I take PSCAD back again. You can find them in the CSMF section of the master library. This is the derivative. So the parameter is, it's asking for the time constant in ST. And it will convert inside to the appropriate discrete controls. So this is the normal continuous domain or S domain component, and these are the discrete domain implementation of the real pole. This has an option like you can select whether the input is already in the discrete domain or the continuous domain. If it is continuous, it will sample depending on the fire impulse or the clock pulse and generate the output. And if it is already sampled, then it will just take this current signal out and do the processing. So the execution of this is dependent on the this clock signal. So it is independent of the time step of the time step you are using in your project. If you have the Z domain coefficients uh, of a digital control, then the easiest would be to use the nth order transfer function. It will ask for the coefficients of each Z coefficients of each item in the numerator and denominator. And you can also connect them to create a more complete control system. One thing that you have to be careful of using the discrete controls is when you have a feedback loop. There's a one-time step delay where the feedback uh, is created. So you have to compensate for that single time step delay in the feedback path when you're giving the clock signal. In this situation, the easiest would be to give the find the complete transfer function and use the nth order transfer function for the discrete controller. Next group of components I would like to show is sources. In version 5, with the introduction of modified nodal algorithm, now we are introducing dependent sources. So you have the current dependent current source, voltage dependent voltage source, and voltage dependent current source. And it's essentially these three, and this is a specific combination of these ones. Ideal ratio changer is essentially current dependent current source connected the other way, and the voltage dependent voltage source connected the other way in reverse connection. And the current scaling component is a specific configuration of the current dependent current source, so that you can use it to scale measure current and scale it with a known value. Two other components, the users have asked for a three-phase current source that giving there's a new three-phase current source, and also users asked for the harmonic source, current source, and voltage source that they can specify specific harmonics with different magnitudes and different phases. So what we have done is, instead of creating two separate sources, we created the harmonic signal generator where you can specify the different number of harmonics with different magnitudes and different phases. And the output of this component can be connected to a current source or voltage source to generate a harmonic current source or a harmonic voltage source. You can find the components in the sources section of the master library. This is the three-phase current source and the harmonic signal generator. And you can use it with the externally controlled current source or a externally controlled voltage source to create the harmonic current source or the harmonic voltage source. These are the dependent source models, voltage dependent voltage, current dependent current source, voltage dependent current source, the ideal ratio changer, and a current scaling component. These components, you can either use it in a single phase or three-phase mode with a choice parameter. So this is the current dependent current source configured in the simple example, configured in the three-phase setting, three-phase current source, and this measured current is multiplied by 0.5 and injected on this side. And there's no time step delay from the measurements to the current injection. And similarly, here the voltage dependent current source, this voltage is measured, multiplied by 0.5, and the current is injected on this side. And the voltage dependent voltage source, the measured voltage is injected with a given scaling factor. And this is the ideal ratio changer. So the current coming from this side is scaled by the current coming from this side is scaled and injected on this side, and the voltage measured on this side is scaled by the same number and to control the voltage source on this side. So this is would be more like a perfectly ideal transformer. This is an example of a solar farm. What we have modeled is just one converter of the solar farm, and the current coming from here is scaled accordingly so that the current, the output of this is the product, this current multiplied by the scale. So this is the you can see the total P and Q coming on this side, but inside before the current scaling component, this is the P and Q. So this is the harmonic signal generator used to control the instantaneous current of the current source, and is the FFT output of this signal. 100. This is in the 110 and 0.1 or 0.1, 0.8, and 100. Next set of components transformers, we introduced a new transform model based on the duality principle. So you can find it in the transform section. It is this component. So you have the select a different core configuration, and also when you're modeling the magnetization branch, depending on what kind of data you have, there are several options you can use. And it also has an option to include stray capacitances, and it can also include leakage values dependent on the tap position. And one other thing is you have the option to enter the select all the vector groups in the transform component. So depending on what you have, you can choose what you want from here. If it's my delta, the list automatically changes, and you can pick the appropriate vector group. Another component is the single phase transform model that can be configured for number of windings between 5 and 12. There's a new intermediate library in version 5. So if you go there, and you can find more transform components that is not fully finalized. This is again based on the duality principle, but three winding transformers for different core configurations. And there are some specific higher number of winding transformers over here. And these three transformer components are essentially the classical transform model we have in the master library. The only difference is this has a support for vector groups. Next group of components I want to show is machines. We now have a single phase induction machine in our machines library, and we have modified the synchronous machine model so that you can have saturation on both D and Q axis. A permanent magnet machine model is modified so that you can have access to the neutral. And then we added IEEE 2016 standard compatible exciter models. While it is running, so this is the synchronous machine model. The option for the saturation, just you can enable only on D or on both axes. And the permanent magnet machine model, there's the external connection to the neutral. And this is the single phase induction machine. It's compatible with the multi-mass model. And the new exciter models, the 2016 standard exciter models, on the far right end of in the page, the AC type exciters, DC type, static type. And if you want the older standard, the models are at the bottom right corner. So this is the single phase induction machine example. So next, I would like to show new passive elements that we changed and new ones. There's a new hysteresis reactor model. You can choose the basic hysteresis for the Chai-Saturn hysteresis on hysteresis reactor model. Existing suchable reactor model has been modified to include so that you can enter data in also in the BH form. The fixed load has been improved to make a composite load which can have up to 3 parts, and the fixed load can be scaled on the run. And there are four new components to model unbalanced delta and Y loads. And there's an electrical tap so that you can tap a single phase or a subset of phases from a multi-phase system. If you go to the passive element section of the master library, this is the hysteresis reactor model. Option for basic or Giles-Atherton. And the searchable reactor being changed so that you have another option to enter data, BH values. And this is the electrical tap component I talked about. You can tap a single phase or a subset of phases from this component. And these are the new unbalanced delta Y loads. This is a delta load, and each branch here you can have a purely resistive, inductive, capacitive, RL, RC, LC, or RLC, or you can keep it open. And each branch you can specify what the parameters are. And this is again a delta connected load, but this one has each leg has 3 branches connected like this. 2 parallel branches in 1 branch in series. And similarly, you can individually specify the values for those components. This is the same concept, Y-connected load, single branch, or a 3-branch one Y-connected load. And the load model, so now you can specify the number of parts in the composite load. You can have up to 3, and then you can specify what is the portion of the power coming from each part of the composite load. And as a scaling factor, you can change it on the run. It's a variable. Next group of components I want to show is the related to breakers. There's the TRV envelope generator. You may have seen this in the intermediate library of POSIX. And there's a new component, isolation switch. You can select open or close. It's an ideal open or ideal close. And you cannot operate this component during the run. It's not a breaker, it's a isolation switch. And find them in the breaker section. This is the TRV envelope generator and the failure detection component, and the new isolation switch, closed or open. It's over here. This is a simple TRV example. So this one generates the envelope of the TRV depending on the what standard and the TRV class you specify. And then here you can see the TRV envelope and the voltage across the breaker, and there's a violation here, and it's over here, it's detected. It displays over here. Complex numbers in PSCAD version 5. Obviously, there's a complex constant component, and if you have a complex constant, then we need a new component to find the complex conjugate. As appropriate, most of the control components in the CSMF library has been modified to support the complex numbers. And with this, we have to also modify the type conversion component. So if you want to convert from real to complex between any two types, the type conversion or the unity component supports that. With that, we also modify the unity component so that if the two sides are of the same type, you can use it to create an array from a scalar. So this is the complex example. The color of a complex signal is in orange. So here the type conversion unity component, you can convert to or from complex numbers using three different methods. You can use the rectangular coordinates or polar coordinates based on radian, or polar coordinates with degrees. So here the complex signal is generated, and then again its complex signal is broken back into real, imaginary, or the magnitude phase values. And here is the complex conjugate component. Putting 0.6 and 0.8 and getting 0.6 and minus 0.8. And for example, I just picked two control components, square root and square. So one angle 90 degrees, square root, you get one angle 45. And 0, 1 complex number, squared you get minus 1 and 0. The complex constant is here, and the complex conjugate is here. Here. I did not show this in the example. So this is complex scalar value, and this component changes from a scalar to a. It also changes to a. You can change it to an array. So in this case, a two-dimensional array. So the next group of components are controls. We have a few new components: pickup, dropout timer, clock, inverse clock, deadband, backlash, and component to detect a change in a signal. And if you want to change one set of coordinates to another set of coordinates, you can use the scale changer and discretizer. And the sort of, you have seen it in the when I went through the MNC components. And we have updated the FFT component so that now it's supposed up to 1023 harmonics. CSMF. So this is the scale changer. So you can give the slope and intercept for the to translate from one side to the other, or you can give 2 points to do the transfer. Essentially, this is more like a scale changer, but this is discrete signal coming out from the other side. And here's the deadband component, backlash, pickup, dropout timer, and change detector. So if it is not an integer, then you have to give an tolerance for the detection to work. So if, for example, if you have a real signal and if the signal changes more than 1e minus 20 right now, it will give an output, generate a signal on the output. What I would like to show is the FTNE component. FTNE component improved, so that now it has power injections enabled. So it's not just giving the equivalent network. You can specify the amount of power that you want to come out at the point of connection, and then it's read from a file, and the power is maintained with the so that you have the same as the original network. And we have introduced passivity enforcement. This will take care of the instability issues created by failures in the passivity violations by enforcing the passivity. The number of frequency samples, that limit, the previous limit has been removed. And the FTNE component, now it is compatible with the frequency scan component. If you're doing a frequency scan of a system that has the FTNE component, the complete effect of FDNE is considered in the frequency scan when you're doing another frequency scan of that network. FDNE component is in the passive section of the master library. It's in the far right end, and there's the options to enable power injections, and you can give the in a file, and then there's an option to enforce passivity. This is the example using the FDNE component. It's a reasonably large system. The area in the shaded that's what we want to model in the FDNE component. Just pay attention to these powers, and this is the same example in the with the shaded area represented by FDNE with the power injections enabled, and the same power is maintained on the at the connecting point. And there's an even further improved FDNE component in the intermediate library of version 5. This has additional curve fitting options. Especially this, the fast relaxed model vector fitting fits the curve on the eigenvalues, so that accuracy of both y and z is maintained. The other methods only considers the y values for fitting the curve. Next, what I want to show is improvements done to transmission lines and cables. Now you can, in version 5, you can have cables and transmission lines in the same right of way. There's an option to enforce passivity. And there's a more accurate extended earth return formula introduced. This will improve the stability in aerial cables. It is especially important for GIS studies with short lines. And the cable loss it's a more accurate cable loss representation. It is part of the insulator properties. Previously, we just had a simple asking for a conductance value to represent the loss. And we have increased the maximum number of conductors in a single right of way. So this is an system which system that has both cables and transmission lines. You have to use the cable interface to model both transmission lines and cables. And at the interface, the first conductors or the first cables are for the cables, and the next set of cables, uh, next set of conductors in the cable interface for the overhead lines. So this is showing the induced voltage on the underground cable when the overhead line is energized. With the uh, with the generalization of cable and transmission lines, now we can also study induced voltages on pipes. So there is a overhead line, and then there's a pipe above ground, and it is checking the induced voltage on the pipe when the transmission line is energized. I come to the end of the webinar. If you have questions, feel free to type in. We'll be here for a few more minutes if you have questions. If not, you can always send an email if you have questions on new models. Thank you. Have a good day or evening. There's a question on double circuit power. Yes, you can have double circuit, or this is even possible in very early versions of PSCAD. Where's the There are different power components. You can use it for double circuit or even more number of circuits.